After studying this module, you shall be able to know how to calculate the lambda max, learn how to find the double bond equivalence, correlate spectra with structure of the compounds, interpret the spectroscopic data. The knowledge and concepts of ultraviolet, infrared, 1 proton NMR, 13 carbon NMR and mass will help us in solving various problems based on the experimental data. This experimental data will help us in elucidating the structure of organic compounds. While analyzing the data, the points must be kept in mind. Number 1, from the molecular formula, one can find out the double bond equivalence or index of hydrogen deficiency. Double bond equivalence, which is equal to 2A plus 2 minus B minus D divided by 2. Here, A are the number of carbon atoms, B the number of hydrogen or the monovalent atoms, number of nitrogen or the trivalent atoms is represented by D. Double bond equivalence is an important factor for determining any organic compound structure. It helps us to understand what are the number of the double bonds present in the compound or the number of the cyclic structures. Lambda max value from UV spectroscopy gives information regarding the presence of conjugation, carbonyl groups, etc. or other information which is obtained from the UV spectroscopy. The IR data gives information regarding the functional group presence and in the given molecule. The splitting pattern, singlet, doublet, triplets, quartets or multiplets in the 1H NMR tells us the number of the neighboring hydrogens present. From the carbon-13 NMR, we get information about the type of carbon atoms. Mass data will give us the information about the total mass of the molecule. Types of fragments present, presence of chloro, bromo or the other atoms. Combination of all these informations gathered will help us to find out the structure of the organic compounds. Now, let us look at certain examples and their solutions which will help us to find out how are we able to correlate and collate all the informations and find out the structure of the organic compound. Let's start with some of these simple examples. Calculate lambda max for the compounds. The lambda max can be calculated using Woodward-Fieser rules as already been explained to you in the earlier modules. Let's look at the example. As we can see here, the base value of the given organic compound is to be taken as 215 nanometers. This is taken as a base value for the alpha beta unsaturated carbonyl groups. The compound shows an extended double bond, therefore the double bond extension of the 30 nanometer value is added into the base value. The substitution of the alkyl group at the delta position adds on another 18 nanometers to the base value. The system is a homodiene system, therefore homodiene means we have the two double bonds in the same ring. Therefore, the value of 39 nanometers is further added. All of them added on together gives us the lambda max as 302 nanometers. Let's look into another question. Example is an alpha beta unsaturated system where the base value now will be taken as 202 nanometers. Question arises, why would we have it as 202 nanometers? Now this can be understood by the fact this is a cyclopentane system. Cyclopentanone system will be showing a base value of 202 nanometers. The alpha bromo substituents add to the another 25 nanometers. Two alkyl groups at the beta position gives the another add-on value of 24 nanometers and the exocyclic double bond is 5 nanometers. This exocyclic double bond is basically the double bond in the alpha beta unsaturated system which is adjacent to the cyclohexane system. That is the cyclic 6-membered ring system has a double bond exactly adjacent to it. Therefore, we add on the value of exocyclic olefinic system. So, the lambda max of 256 nanometer is recorded for this given example. Now, these values were found to be very much in accordance with what we observe as an experimental value. The next example is again an example for an alpha beta unsaturated system, wherein again we see the base value of 215 nanometers. It is double bond extensions, which is little different from what is double bond equivalence. So, here in these we are all considering the double bond extensions. These are all due to the presence of the extended double bond systems. So, here we have two double bond extensions which adds on the value of 60 nanometers, 30 for each of them. We have a alkyl extension at a beta position. So, the value of 54 nanometers for that. We have three alkyl groups at the gamma positions, which is 39 nanometers, and the three exocyclic double bond systems, which another adds on to the value of 15 nanometers, and that makes a total of 356 nanometers as the lambda max value for this organic structure. Let's look into this example. Now, this example is little different from the other ones. This is not an alpha beta unsaturated carbonyl system. This is a conjugated diene system. Now, conjugated diene systems could be of two kinds. It could be a homodiene or a heterodiene system. However, this specific example deals with the system which has both the options, homodiene as well as a heterodiene. However, as a principle, we always try to take a system which has a higher base value. So, here the homodiene system with a base value of 258 nanometers is taken as a standard. Here again, as I said, we have to add on the value of the double bond extensions, which is an extended double bond systems in the given organic structure. We can see two extended double bonds, therefore that gives in a value of 60 nanometers. There are 6 alkyl groups which are at the different positions and the extensions to the given diene system. So, that adds on to the value of 30 nanometers, which is 5 nanometers for each of them. 3 exocyclic olefinic systems add in another 15 nanometers makes a total of 358 nanometers as the lambda max for the given organic structures. Question number 2. Match the 1 proton NMR spectra with one of the substances. There are a number of structures given, and what we have to identify is which is the structure which actually matches with the given NMR spectroscopic data. Here, as we can see, the data calls in for a triplet at 9.72 with the coupling constant of J is equal to 2.1 Hertz for 1 proton. There is a doublet at 2.36 delta value with the coupling constant of 7.1 Hertz and 2.1 Hertz for the 2 protons, and a multiplet of 1 proton at 2.21 delta value. Doublet is also seen at the value of 0.98 delta with the coupling constant of 6.7 Hertz for 6 protons. How do we primarily explain the given data and correlate it with the given compounds? A peak at 9.72 ppm, which is a very downfield value, is for an aldehydic proton as it is connected to a highly electronegative group. Now, this peak indicates the presence of 2 hydrogens adjacent to these carbons. Doublet at 0.98 is indicative of 6 protons, which shows the presence of an isopropyl linkage. Now, this isopropyl linkage has the 2 equivalent methyl groups, which should be in turn linked to one CH group, which shows the doublet. Now, this is assisted by the multiplet at 2.21 ppm for one hydrogen. This hydrogen is adjacent to another carbon bearing the hydrogens. A peak at 2.36 is observed as a double doublet for 2 protons indicate the presence of a CH2 group between isopropyl and the aldehydic groups. Now, if we try to correlate all the data and see, we observe that this structure, this data matches with the structure of the compound A, which is CH3, CH3, CH, CH2, CHO. Next question. A given organic compound has a molecular formula C7H12O3. The NMR spectroscopic data shows the peaks at 4.15 quartet for 2 protons, a triplet at 2.7 delta value again for 2 protons, 2.55 a triplet for 2 protons, a singlet at 2.2 for 3 protons, and triplet at 1.25 for 3 protons. Carbon 13 NMR spectra shows the peaks at 10, 28, 31, 38, 62, 172 and 208 ppm. The IR absorptions are observed at 1710 and 1750 centimeter inverse. Now, to solve the questions like this, it is really important that first we have to find out the double bond equivalence of a given compound. As can be seen from the formula, 2A plus 2 minus B minus D divided by 2 is the formula for finding out the number of double bonds or the cyclic structure in a given organic compound. Therefore, if we try to analyze the formula, A is the number of carbons, B is the number of hydrogen or the monovalent atom, D is the number of nitrogen or the trivalent atoms. Substituting all the values, we find that the double bond equivalence for the given organic compound works out to 2. This shows the presence of 2 double bonds. Since there are 3 oxygen atoms, so we assume that there may be 2 carbonyl groups. And for this, we check it with the carbon 13 NMR to compare it. The peaks at 208 and 172 ppm value proves that there are 2 carbonyl groups. Now, the peak at 208 in the 13 carbon spectroscopy for the carbonyl group is for a ketonic group, and at 172 ppm is for the carbonyl group, which is then probably a carboxylic acid group or a carbonyl group, which is could be even an ester. 1 proton NMR and the 13 NMR data also indicate the presence of 12 protons and 7 carbon in the molecule, which is in quite a correlation with what we have seen in our molecular formula. By NMR, we have been able to find out that there is one OCH2 group, one CH2CH3 group, a carbonyl group and a C carboxyl groups. Peak at 2.25 for 3 protons indicate the presence of COCH3 group. 2.25 is normally an indication of a methyl group, which is linked to the carboxyl group. By combining all these informations together, we have been able to come to the conclusion for the given structure to be that for ethyl levulinate. The structure calls in for CH3, CO, CH2, CH2, C double bond O, O, CH2 and CH3. Let's look into the next parameter, how to calculate the chemical shift for the carbons in any of the examples. For the convenience, we have taken an example of a compound CH3, CH, CH3, CH2, CH2, CH3. For acyclic compounds, the chemical shift for the carbon 13 NMR can be calculated from the formula 1 plus 7x1 plus 8x2 minus 2x3 plus minus the value of 4 ppm. Here the x1 is the number of carbon atoms 1 bond away, x2 is the number of carbon atoms 2 bond away, and x3 is the number of carbon atoms 3 bond away. For C1, delta value will be 1 plus 7 multiplied by 1 because there is only one carbon atom which is away by one bond, plus 8 into 1 minus 2 into 2 which is equal to 12 ppm. For second carbon atom, the delta value will be 1 plus 7 into 2 plus 8 multiplied by 2 minus 2 multiplied by 1 which is equal to 29 ppm. For the third carbon atom, the delta value is 1 plus 7 multiplied by 3. Again I repeat, as we can see from the structure, there are 3 carbon atoms which are 1 bond away, plus 8 multiplied by 2, as there are 2 carbon atoms which are 2 bond away, and 2 multiplied by 0 as there is no carbon atom which is 3 bonds away, and that makes a total of 38 ppm. For 6 carbon atom, delta value is 1 plus 7 multiplied by 1, 8 multiplied by 2 minus 2 multiplied by 3 which is 18 ppm. This is how we calculate the chemical chip for the carbon 13 compounds. Next question. A compound of molecular formula C6H10O shows an absorption at 1720 cm inverse in IR spectroscopy. Its NMR and 13 carbon data. 1 proton NMR shows the peaks at 2.0 3 proton singlet, 2.5 a 4 proton multiplet, 5.0 a 2 proton multiplet, and 6.0 a multiplet for 1 proton. A 13 carbon NMR shows 28, 29.7, 42.7, 115, 137.6 and 206.6 ppm values. Again, as a principle for solving all these questions, first we find out the double bond equivalence. The double bond equivalence as per the formulas which have been explained to you earlier is found to be 2. Double bond equivalence shows the presence of 2 double bonds. In 1 proton NMR data, spectroscopic data which we have been given to us, the 3 protons at 2.0 ppm indicates the presence of COCH3 group. The IR absorption at 1720 cm inverse proves the presence of a carbonyl group. The 4 proton peak at 2.5 ppm value in the NMR spectra indicates the presence of CH2. Now since these are the equivalent protons, therefore they all appear as a singlet. The resonance at 5.0 and 6.0 ppm indicates the presence of the alkene system. The presence of CH double bond CH2 unit is confirmed by 13 carbon NMR spectroscopic data at 115 and 137.6 ppm. Henceforth, again the structure of this compound, as we can see from all the spectroscopic data which we have till now, will be CH3, CO, CH2, CH2, CH, double bond CH2. A compound has a molecular formula C6H11BrO2. Its carbon 13 NMR data is given to be 173.4 singlet, 51.5 quartet, 33.1 triplet, 32.9 triplet and 23.5 triplet. Now this is a data which shows us the splitting, as this is a coupled spectra for the carbon 13 for a given compound. Again, double bond equivalence was found to be 1, which most likely either shows the presence of a double bond or a carbonyl group. The presence of the carbonyl group is confirmed by the peak at 173.4 in 13 carbon NMR. Thus, it accounts for only the double bond present. From carbon 13 NMR, it is concluded that peaks at 173.4 is for the carbon attached to no hydrogen, which is a carbonyl group, and 51.5 is for the carbon attached to the 3 hydrogens, which are CH3. Therefore, these two peaks together indicate the presence of the structure, which is C double bond O, OCH3. Triplets at 33.1, 32.9 and 23.5 indicate the presence of 3 CH2 groups, that is CH2, CH2, CH2 group in the molecule. So, the final structure of the compound works out to be Br, CH2, 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 C double bond O, OCH3. Now we have to match the compounds with the spectrum of the given values. Here in all these examples, what we observe is that the coupling constant is different for the different spectra. As a matter of fact, what we have to do will be to correlate the coupling constant with the given structures. As we can see, the first structure shows the coupling constant as 9.0 Hz. Second does not show any coupling constant. Third shows a coupling constant of 1 Hz. And the example D, the spectra shows the coupling constant of 2.4 Hz. An exchange in deuterium oxide is for the phenolic hydroxyl group present in all the molecules. In the NMR sample of the compound A, the coupling constant is 9 Hz. It means it is an orthocoupling. In the NMR of sample C, the coupling constant is less than 1 Hz. It means it is a paracoupling. And in D, the coupling constant is 2.4 Hz. It means it is metacoupling. In NMR of the sample B, there is no coupling observed. Thus, the equivalent hydrogens are present. Looking at the above values, we can elucidate the structures to be B, C, D and A in a sequence of the given structures. How the number and position of carbon 13 NMR signals can help in the identification of 4 isomeric alcohols in the compound C4H10O give the structure of each alcohol. The given alcohol molecular formula would be having 4 isomers, so we have to primarily identify the different structures through the spectroscopic data. The first isomer CH3, CH2, CH2, CH2OH has 5 signals, that is a hydroxyl group at the position number 1. The moment the hydroxyl group goes at the position number 2, it would show us 5 signals, 1 singlet for 3 hydrogens. The third isomer with the methyl group as a substituent, that is CH3, CH, CH2OH, and the methyl group at the position number 2 has 4 signals, doublet for 6 hydrogens. CH3 whole thrice OH shows 2 signals, singlet for 9 hydrogens, which will be the isomer number 4. Proton and 13 carbon NMR data of 2 compounds C5H8O and C5H10O is shown. The compound A shows the spectroscopic data with the NMR values at 1.20 delta value with the 6 protons and a singlet, 1 proton singlet at 2.6 delta value and 1 proton singlet at 3.2 delta value. 13 carbon NMR data shows the peaks at 45, 68, 72, 85 ppm values. The IR shows the absorption at 3300 centimeter inwards. The compound B shows the spectroscopic data as follows, wherein we can see the data shows the peaks at for 6 protons, singlet at 1.25 ppm, 1 proton singlet at 3.3 ppm, 2 proton multiplet at 4.8 to 5.1 delta value, and 1 proton multiplet at 5.7 to 6.0 delta values. Carbon 13 NMR shows the peaks at 44, 72, 110.73, 146.48 ppm. The IR absorption shows the peaks at 3300 cm inwards, and the peak at 3.2 and 3.3 disappears on shaking with deuterium oxide. Determine the structure of the compound. Again, to solve the questions, we go in for the finding of double bond equivalence. It was found to be that double bond equivalence is 2. Peak at 1.20 ppm singlet for 6 hydrogens indicate the presence of the 2 methyl groups. Peak at 3.2 ppm singlet, 1 hydrogen and disappears on shaking with deuterium oxide indicates the presence of the hydroxyl group. Henceforth, we assume that the structure of the given compound should be CH, triple bond C, 2 methyls with COH, and for the compound B, double bond equivalence was found to be 1. Peak at 1.25 ppm, singlet for 6 hydrogens indicate the presence of the 2 methyls. Peak at 3.3 ppm, singlet for 1 hydrogen, which again disappears on shaking with deuterium oxide, indicates the presence of the hydroxyl group. Peaks at 4.8 to 5.1 multiplet for 2 protons and 5.6 to 6.0 multiplet for 1 proton indicates the presence of the alkenic hydrogens. This is very specific for the alkenic hydrogens. Therefore, we can assume the structure to be CH2 double bond CH, COH and 2 methyls. Henceforth, the two data, the spectroscopic data, are very conveniently able to elucidate the structure of the two compounds with the given molecular formulas. A compound C8H8O2 shows an IR absorption at 1685 cm inverse, and the data is provided to us. 1 proton NMR, 3.9 singlet for 3 protons, 7.0 doublet with a coupling constant of J is equal to 9 Hz for 2 protons, 7.9 doublet with the J or the coupling constant for 9 Hz for 2 protons, 9.9 singlet for a proton. 13 carbon NMR shows the peaks at 555.6, 114.5, 130.2, 132.2, 164.9, 191.0 ppm values. The mass spectroscopy shows the fragments and the peaks at 136 as a base peak, 135, 107, 92 and 78. We have to deduce the structure of the compound and account for all the observations. Double bond equivalence for the compound is found to be 5. IR of 1685 cm inverse means a carbonyl group is present in conjugation. 1 proton NMR, 2 doublets of 2 hydrogen each with the coupling constant of J is equal to 8 Hz means a para-substituted phenyl ring is present. A singlet at 9.9 ppm confirms the presence of an aldehydic group. Singlet for 3 hydrogens at 3.9 shows the presence of OCH3. Henceforth, the structure is found to be as follows. A compound has a molecular formula C6H10O2. 1 proton NMR shows the peaks at delta value of 2 as a singlet for 3 protons, 2.4 triplet for 2 protons, 2.7 triplet for 2 protons. A 13 carbon NMR shows the peaks at delta values of 52, 170 and 200 ppm. Double bond equivalence for the compound is found to be 2. A double bond equivalence of 2 means an aliphatic compound with either 2 double bonds or it could have been the aromatic ring. However, the two aromatic ring would have shown a high number of the double bond equivalence, hence the absence of the double bond, absence of the aromatic ring has been confirmed. It is also confirmed by the absence of the peak at 7 ppm in 1 proton NMR spectroscopic data, 125 to 130 ppm in 13 carbon NMR. A 13 carbon NMR peaks at 170 and 200 ppm means presence of the carbonyl functionality. Singlet at 4 ppm indicates the presence of a methyl group attached to an electronegative atom. This is further supported by a carbon 13 NMR spectrum and one peak at 52 ppm. So, the presence of OCH3 group can always be concluded for. Two triplets at 2.4 to 2.7 ppm indicates the presence of a CH2 unit, which in turn are attached with an electron withdrawing group. Presence of an electron withdrawing group on the either side of CH2 and CH2. A presence of a 3 proton at 2 ppm indicates the presence of CH3 functionality attached with an electron withdrawing group. So finally what we can see is an electron withdrawing group along with the CH3 group. Further, presence of a peak at 170 ppm and 200 ppm indicates the presence of a carbonyl function. So, looking into all these above parameters, we can conclude the correct structure for the compound to be CH3, CO, CH2, CH2, C double bond O, O, CH3. A compound has a molecular formula C10H18O2. From the proton NMR spectra and 13 carbon NMR data, identify the compound. Carbon 13 NMR data shows a singlet at 166.4, a doublet at 149.0, again a doublet at 18.2, a triplet at 59.7, triplet at 39.2, a doublet at 32.4, a triplet at 20.7, a quartet at 20.2, a quartet at 14.2 and a quartet at 14.1. The 1 proton NMR data shows our double doublet at 5.92 with the coupling constant of 7.9 Hz and 11.5 Hz for a single proton, 5.68 doublet with the coupling constant of 11.5 Hz for a single proton, peak at 4.15 ppm with the quartet with the coupling constant of 7.2 Hz for 2 protons, a multiplet at 2.40 ppm for 1 proton, a triplet at 1.27 ppm with the coupling constant of J is equal to 7.2 Hz for 3 protons, a peak at 1.2 to 1.3 delta value for 4 protons as a multiplet, doublet at a value of 0.99 with a coupling constant of J is equal to 6.6 Hz for 3 protons, peak at 0.88 as a triplet with the J value of 7.1 Hz for 3 protons. The double bond equivalence for the given compound is found to be 2. The substructure associated with the carbon 13 NMR is a disubstituted alkene. It accounts for 1 double bond. So, therefore, the structure can be assumed to be CH double bond CH further linked to the other substituents. The substructure associated with the carbon 13 NMR is carbonyl group. This accounts for the second double bond. Therefore, we can assume the structure to be a carbonyl group linked to a further oxygen, which in turn is linked to the other carbon atoms. The peak at 4.15 ppm for 2 proton means the carbon is attached to oxygen atom as a signal is a quartet. It indicates the presence of methyl group next to it. The substructure associated with this 1 proton NMR is C double bond O, O, CH2 and CH3. As we can see that this is able to show a quartet at 4.15 with the coupling constant of 5 to 7.2 Hertz. Similarly, for the other methyl group, which is the 1.27 triplet with the coupling constant of 7.2 Hertz. The coupling constant of J value to be 11.5 and 7.9 Hertz are for the cis protons and the vinylic protons respectively, as shown in the given structure. The structure of the compound therefore is concluded to be CH3, CH2, CH2, CH2 with a methyl as a substituent, and then the olefinic group attached to a carbonyl group and an oxygen with the ester group. Dear students, after doing n number of questions, now I am sure you would be confident enough to decide and see how can you correlate the data from one kind of a spectroscopy and the other spectroscopic techniques, and together combine them to deduce a structure of an organic compound. Let's understand that firstly, the double bond equivalence finding for any structural elucidation is a prime rule which will help us to understand what are the number of the double bonds which are present, or the cyclic structure, or whether the compound is aromatic or it is a non-aromatic compound. The IR data helps us to find out the functional groups present in it. The UV spectra has been able to help us to find out the conjugation in the given organic compounds. NMR and C13 data have been able to help us understand the chemical environment of the protons which are present along with the different type of the carbon atoms which are there in the organic compound. However, now the onus lies on to you how to correlate, how to interpret, and how to relate all the data together to find out the organic structure.